To start out the second half of Chapter 14 in the evolutionary solver, we have to know what non-smooth optimization models are. The definition from the book states that non-smooth optimization models are models that violate the linearity conditions required for the linear optimization solution method used by solver. A few functions that can lead to non-smooth optimization models are if, abs for absolute value, min, and max. An issue that can arise with non-smooth optimization models is that they can be difficult to solve using conventional techniques. So to fix this, the approach called meta-heuristics was developed, and it has a few approaches such as genetic algorithms, neural networks, and taboo search. In the broad approach that is in meta-heuristics is heuristics itself, which are intelligent rules for systematically searching among solutions that remember the best solutions they find and then modify or combine them in attempting to find better solutions. It's important to note that the evolutionary algorithms can be used with the if function in Excel to model fixed costs, and this is something that I'll go over on the next slide. So example 14.11 deals with K&L designs from chapter 13, and the business incurs a fixed cost of $65 for 3 months of rent. It has equipment that can be rented or returned each quarter, and this idea of being able to return the equipment is something that will involve the if function that I explained before, because if the business doesn't produce anything, then they're able to return the equipment and therefore will not incur the cost of it for that month. For example, if the company did not produce anything during a quarter, then they could return the equipment, but if they do produce, they would have to incur the cost. Hopefully this shows the importance of the if statement that will be involved with the evolutionary solver. Also, from the picture of the equations, there are upper and lower bounds, which is required when using the evolutionary solver in order to restrict the search space to be more manageable. The idea of making the search region more manageable relates to the next idea that I'll talk about with the evolutionary solver. Since evolutionary solver is a search procedure, it can sometimes be unable to provide the optimal solution on the first time around. This is because it can be affected by inferior or an infeasible solution, which may not be the most ideal outcome. However, this is why it's important to run the evolutionary solver a few times, because doing so will help the user to reach the most optimal solution. With the evolutionary solver, there are a few factors that can impact the results, such as the starting values of decision variables and the amount of time that's devoted to the search. In order to help reach the most optimal results, changing these factors may be helpful. For instance, increasing the time that is taken to find the optimal solution could improve the solution itself. Also, with a complex problem, changing the input values and other parameters could change the solution that's received. The evolutionary solver tool on Excel can also have a practical application with job sequencing, which Alicia will talk about next.
Okay, so to begin, as introduced in Chapter 11, a unique application of Excel modeling and evolutionary solver is for job sequencing problems, and we are going to use the model we already looked at in Chapter 11 to show this. Job sequencing problems involve finding an optimal sequence or order to process a set of jobs. As seen here, the example from 11.17, we had a spreadsheet model for the following scenario. Supposing that a custom manufacturing company has 10 jobs waiting to be processed, each job, I, has an estimated processing time, PI, and a due date, DI. That was requested by the customer as shown in this table. Our goal is to find a permutation that optimizes the chosen criteria. Solver has an option to define decision variable as a permutation. This is called all different constraint. To do this, open the Add Constraint dialog, choose the range of the decision variables, and then choose diff from the dropbox as shown here. This final model, you are to minimize the chosen objective cell, in this case, the total tardiness, and ensure that the decision variables are a valid permutation of the job numbers. And lastly, in this slide shows the solution of the solver. Now Noah is going to discuss the traveling salesperson problem.
The traveling salesperson problem is described as a salesperson that needs to visit each different city and return home in the minimum total distance. The route that the salesperson uses to visit each city exactly once and then return to the start is called a tour. An example of this theory are delivery drivers for companies such as FedEx and UPS. They must deliver packages to return to customers all day and return to their central location like a warehouse or an HQ. Soft drink vendors also use this to go out and collect money from certain vending machines before returning back to the warehouse as well. A simple shopping trip could even be considered as a tour. Another example is a programmed drilling machines used to drill holes in circuit boards and picking orders within a warehouse, such as a CNC machine. The machine is programmed to complete these tours, then when finished drilling the holes, the machine goes back to its original state. Within all of these tours, the goal is to perform the task in the most efficient way possible and in the minimal total time and distance. Here is a video that goes in more depth of the traveling salesperson problem.
Imagine that you're on a shopping trip where you need to visit 8 shops. There's a path between any 2 shops, but the distance varies depending on the shops. You need to start and end at the same shop and visit all of the shops exactly once. This is called a Hamiltonian cycle. Let's say you're in a hurry. What's the shortest cycle you could take? This everyday dilemma is so important that computer scientists have crowned it the Traveling Salesman Problem, or TSP. Let's first consider these 4 shops, numbered 1 through 4 here. Making sure to visit all shops exactly once, one path we could take starts from shop 1, moves around to 2, 3, and then 4, returning back to 1 for a distance of 17 miles. We could switch up the order we visit to get more paths. But how many paths are there? There are 4 shops to start off. For each of those 4 shops, we have 3 choices to visit next, then 2, then 1, so there are 4 factorial, or 24, paths to check. It's easy to list all 24 of these paths, calculate the distance for each, and find the shortest, which is 17 miles for our example. What about n shops total? That would leave us with n factorial paths. For even slightly more cities, the number of paths increases to dangerously high numbers. How about 50 cities across North America? We're already buried under this many paths. It's unmanageable. So what do? Well, do we always need perfect solutions? In practice, often we just need good enough solutions, but quickly. So we use heuristics. Heuristics find approximate solutions by ignoring bad paths right off the bat instead of checking each one. Humans already use heuristics naturally. For these cities, our intuition tells us that the shortest route should be close to this. Maybe it's not the best, but it's definitely close. And with one look, we know that a route that begins like this likely won't be the shortest, so we don't even consider it. A simple heuristic is the nearest neighbor heuristic, which starts at a random city and always chooses the closest, unvisited neighbor until we end up back at the start. Using this, we only need to go through all of our cities once, and for each city, check all of its neighbors once, so the worst case performance is n squared, or only 2,500 steps or 50 cities. A lot better than our previous monstrosity. Ultimately though, heuristics only approximate solutions, and while nearest neighbors is extremely fast, it's not very accurate. For some cities, it even gives the worst possible path. A better choice is what's called ant colony optimization, where we simulate a swarm of virtual ants exploring our cities. The probability of an ant moving from one city to another depends on the attractiveness of the move, typically the inverse of distance, as well as the amount of pheromone present. Putting it all together, we get this formula. The numerator is for the move we are considering, A to B, and the denominator is the sum of all possible moves from A. But where does this pheromone come from? When an ant completes a cycle, it leaves some pheromone along the path. Shorter cycles leave larger amounts of pheromones than longer ones. This way, with enough ants, we can guide them to find shorter and shorter cycles. With these short paths, TSP can approximate optimal transportation routes, build microchips, and also map telescope placement in astronomy. And if we think of distance as similarity between DNA fragments, we can even use TSP for DNA sequencing. Who knew?
Lastly, Lindsay is going to talk about the case study for this chapter.
The case study for this chapter discussed how to apply nonlinear optimization to portfolios. Prudential Securities Incorporated created a mortgage-backed securities department in which they developed a variety of models, including linear, integer, and nonlinear optimization. Nonlinear optimization was used to construct optimal portfolios for clients. Investment portfolios were put against a variety of interest rate scenarios in order to identify which scenarios would work the best. The analysts were then able to generate an optimal portfolio that is diverse and matches the investor's performance profile. To summarize, the main purpose purpose of portfolio optimization is to maximize returns and minimize the risk of a portfolio of assets according to modern portfolio theory. Here we have two discussion questions. First, what is a scenario analysis? A scenario analysis is a process of examining and evaluating possible events or scenarios that could take place in the future and predicting the various feasible results or possible outcomes. Our second question is, how would you use the traveling salesperson problem in your everyday life? And we want you to answer this question on the discussion board.